Hello, everybody. Welcome to our third colloquium series. So it's my pleasure to introduce David Brady, our new Goodman Endowed Chair of Optical Sciences. Just a little bit about David's history. He's a fellow of OSA, SPIE, and IEEE, and received the 2013 SPIE Dennis Gatter Award for the development of compressive holography. David earned his BA in physics and math from Macalester College and went on to do his MS and PhD in applied physics at Caltech, where his thesis was on the topic of volume holography in artificial neural networks. Before he came here, David was faculty at University of Illinois and Duke University. During lunch today, I learned that he enjoys running, he enjoys sports photography, and may or may not have an interest in Korean pop singers. But today he's going to talk about something near and dear to his heart, neural processing and snapshot compressive imaging.
Thank you. Thanks, Tom. Thank you all for coming today. So I'll go ahead and launch right into today's discussion. So here's what I want to tell you about. I'm going to first of all tell you what snapshot compressive imaging is, or what compressive tomography is. Same thing are. And then, so compressive tomography has been kind of a hot topic, I guess, for 15 years or so. But in the last 5 years, it's been substantially changed by the emergence of neural inference algorithms. So I'll talk about how those have changed compressive tomography. And then I'm going to just talk about a bunch of examples of. It turns out that this problem of tomographic inference is mathematically identical in a variety of contexts, but is applicable to a wide variety of interesting imaging systems. So I'll give you those examples, and then. So I work in computational imaging. Computational imaging consists of joint optimization of measurements and algorithms, deciding what measurements to make based on how the algorithms will produce the image. And so originally the emergence of compressive tomography was based on some ideas from compressive sampling theory that was prior to the existence of neural inference algorithms. And now the existence of neural inference suggests new ways to think about the physical sampling. And so I'll talk about that at the end of today's talk. So tomography means imaging. So the word means slice selective imaging. It means measuring. Tomo is Greek for slices. So originally it was a technology for moving a source and detector in a way that allowed you to pick out a slice from an object. And then computerized tomography emerged, which consisted of basically estimation of multidimensional objects from lower dimensional measurements. These are maybe the most famous original examples in terms of computerized X-ray tomography and magnetic resonance imaging. That's actually a picture of my own skull. They took an MRI of me as part of a photon diffusion study. Some friends of mine were doing things where they shot lasers into your head. And I was hoping after they had a picture of my brain, they'd say, like, that's the best brain we ever saw. But all they said was that I had an unusually transparent skull. So compressive. So tomography, you want to measure a three-dimensional object, and typically the problem is you only have two-dimensional detectors. Compressive tomography means that you're going to get over that by saying, even though you have a two-dimensional measurement, you're going to estimate a three-dimensional object. So snapshot imaging, normally like this CT tomography and MRI tomography, they all work by temporally scanning. That you make two-dimensional measurements, but you make a set of two-dimensional measurements that you can invert to get a three-dimensional object. But that means that you can't make tomographic video. You don't have the ability to measure time because you gave up time to get the third dimension of space. Snapshot imaging means you're not happy with that trade-off. You want to get the full three-dimensional image from a single snapshot. So just to understand what tomography is, this is where my own work with tomography began. Over the last 20-some years, I've been fortunate to build, as we'll see, like a very wide variety of X-ray, millimeter wave, visible tomographic systems. But this was the first tomographic image that I ever published. This one was, I'm pretty sure, the only picture of a toy dinosaur that was ever published in Science. But it was a toy dinosaur that was captured with visible cone beam tomography with the lensless interferometric camera. So you used a rotational shear interferometer to measure the coherence function of the field, and then captured that from a variety of angles. And it's tomographic image because you take the toy dinosaur and you can slice it through the volume and see what the volumetric image looks like. This was not compressive tomography. This was, rotating around the dinosaur, recording a whole bunch of data. This was our first work on compressive tomography. Specifically, what we were interested in was hyperspectral imaging. So hyperspectral imaging is multidimensional because you have 2 dimensions of space, and then the third dimension is spectrum. And conventionally, with the hyperspectral imaging system, you can do what's called a push broom system, where you measure a line in space and in wavelength. So you're measuring a slice, and you can move that slice through space. You can use a filter where you sweep the filter. You get a 2-dimensional image, but 1 wavelength at a time. Those are all continuous manifolds of sampling. An RGB camera, the typical camera in your phone, is a multispectral camera. It does it by mosaic filtering. So each pixel measures red, green, and blue, and then those pixels are processed and combined to create the 3-dimensional tomographic imaging. Here we wanted to do that, but with many more colors than just red, green, and blue. So we built a camera that images a scene, but instead of imaging the scene directly onto a detector, it images onto a coated aperture. And the coated aperture looks something like this. And then it re-images the same scene onto a CCD, but through a dispersive element. So we have this prism that shifts the colors relative to each other. And so on the CCD, you're seeing the original image, but with the color planes sheared, which means you're integrating projections along the color planes. So this is what this kind of system looks like in practice. It's a 4F imaging system, has an initial objective lens and then a re-image onto a detector. By processing the data that you get from this kind of system using a constrained optimization, so we used a lasso algorithm, which is a linear regression with a L1 constraint on the reconstruction. You could reconstruct the entire data cube from a single snapshot. So you record a 2-dimensional image, and from that single 2-dimensional image, we reconstructed about 48 different color planes. So in this particular object, I guess I don't have a picture of the object, but it was like a banana and a stapler and an apple, and so you have the red, green, and blue images are different from each other. Here's a higher quality version of that kind of image. So the data, looks. This is the overall kind of black and white image of the scene. This is the scene as seen with an RGB camera, and then this is the scene as reconstructed with the hyperspectral processing. So you have the green leaves and the red berries. Everything's reconstructed in its own color plane. So the point of the compressive part of the measurement is that we were measuring a coded projection that we can use to do the reconstruction. This is what the coded projection looks like. So one image that you look at looks like this. And so here we have some birthday candles and some flames. And you see this texture. And basically, we're doing a kind of code division multiple access that we're putting each color on its own code. And then we can recognize the code and then reconstruct the colors. And so processing this texture pattern, basically you're assuming that the image has kind of code space available. The image is structured, and so by putting texture on top of the image, you can recognize the texture and get the local color. Now, in this particular case, the point is that by doing the compressive measurement, we can reconstruct video of a hyperspectral system that you might normally have to scan. So this is the birthday candles recorded with an RGB camera. This is the data that we record with this coated aperture double Amici prism system. And then this is the reconstruction of the hyperspectral data cube at video rate. So what you see, in these candles were illuminated with fluorescent lights. So despite the colors you see on the candles, the main color channels that the candle bodies appear in are the spectral channels that are present in the fluorescent light. And then the flames have chemical color, so wherever each flame is present in the color channel, it corresponds to whatever chemical thing is producing that flame. So this is, for us was a very exciting and cool thing. We were, to be honest, I wasn't, hyperspectral imaging is a cool and wonderful thing, but it's not my thing, so I'm happy to make hyperspectral cameras and give them to people. What I was interested in is what is the best way to do tomographic imaging if we don't want to give up, basically, the sort of naive tomographic imaging says, well, I'm going to go just do all this scanning, but from a measurement point of view, when you make measurements, there's a certain cost and a value to each measurement. You'd like to make the measurements in an order that maximizes your information flow so that, for example, you don't have to give up time to get video, to get multidimensional data. So this is really a question about, certainly, is a good way to make hyperspectral cameras, but more importantly is a way to think about how should you make tomographic measurements. So the tomographic measurement system, basically, you have a multidimensional object that you want to estimate, and with this compressive coding strategy, what you do is you go in and find a way to modulate locally within the volume different codes on the different slices. So you're going to tomographic image, you're going to image a bunch of slices. You need to put a different code on each slice so you can integrate all the slices together and then reconstruct that to get the original image. Now, a lot of the things I'm going to show you in today's talk come from a paper that was published in IEEE Signal Processing magazine this spring that was joint between myself and Professor Katsouglias at Northwestern and Xin Yuan, who has been a real leader on the signal processing side of compressive tomography, who was at Bell Labs at the time the paper was written and now is at Westlake University in China. So, this is the kind of coding thing that was in that signal processing paper. When we first started working on these compressive tomography ideas, the algorithms people used to do the inversion were these algorithms with a sparse prior. There's total variation or L1 sparsity. And you use an iterative algorithm, you make some measurement, and you do kind of a reconstruction. In the history of image processing algorithms, there's only like 4 or so, so basically you could do linear inversion. Linear inversion won't work for this, right? If you measure this kind of compressed data, linear inversion cannot give you a good image. And so the algorithms that emerged in the last 30 years were things like total variation and expectation maximization, both of which emerged as kind of denoising algorithms, right? That you had noisy images, and these are algorithms you could use to remove the noise. But engineers being engineers are like, okay, well, we have these great denoising algorithms. Why don't we add noise to help us get better images? So that's basically what we're doing with compressive tomography. We're creating structure that we can use denoising algorithms to recover the image. So basically, if a channel can be fixed, more information can be sent through the channel. But these algorithms are pretty kind of sledgehammers, for a more subtle problem. That basically they're enforcing sparsity on the reconstruction. Where modern algorithm, like a neural algorithm, you can recognize this object has these properties. I want to reconstruct the object based on those properties. And so in the last 5 years, with the emergence of neural processing, a variety of very, very powerful neural algorithms have emerged for doing decompressive inference. So the physical coding stayed the same, but the algorithms have changed. Yeah?
These maps are black and white. Light either goes through them or doesn't.
Yeah, the ones we use in this hyperspectral imaging system, they're chrome on glass binary masks. Depending on the system, you could use halftone masks, or you could use phase masks, and as I'll talk about in some of the different systems to come.
And you mix the color with the mask for each color. You use a different mask.
Well, we use the same mask for each color, and the detector integrates all the colors. But that's why we have the prism. Is basically we have a single mask, but the prism shifts the masks for the different colors, so there's a spatial shift on each color. Okay, so these are different neural algorithms. This E2E, that means an end-to-end training. That basically, you have the input and the output that you want. That works spectacularly well, but assumes that the neural algorithm is highly tuned to exactly the problem that you're trying to solve. You can use neural denoising algorithms, the same as you use general denoising algorithms to do the inversion with the conventional systems. And if you do that, the advantage is that the system generalizes better, that you don't have to train as much. And so I'll talk about some comparison with different neural algorithms during the talk. Here's the amazing thing, is that so originally we developed this and published it for hyperspectral imaging. Now our own group was fortunate enough after that my group applied the same mathematics to all kinds of different X-ray imaging, to holographic imaging, to millimeter wave imaging, to video, to polarization imaging. Those are all just the things that our group did, applying the same mathematics to different tomographic imaging systems. But here's a list of different systems in a whole bunch of different papers that have applied this theory to tomographic imaging in a variety of different contexts. And so the data cube is the multidimensional thing you're imaging. The data cube could be X, Y, and lambda, like hyperspectral imaging. It can be X, Y, and time. It turns out you can think of video as a tomographic thing. And of course, there are groups that have done ultra-fast imaging, where you could do nanosecond scale, picosecond scale imaging by using this same coding strategy. You can do this XY plus Z is simpler than XYZ. That's assuming that two-dimensional images with range. So you do depths from defocus, stereo imaging, stereo X-ray. Certainly, so there's three broad classes of tomography: of projection tomography, like with X-rays, diffraction tomography, like with radar and holographic imaging. And so there's many classes of different kinds of diffractive tomography that have used the same basic mathematics. And then you can get into 5 or 6 dimensional imaging if you include wavelength, polarization, and time. All of these different things use the same coding strategies and the same kinds of inversion algorithms. And then you could look, this is different kinds of physical systems that have used this, and then different kinds of algorithms. Originally, most people would have used just the sparsity algorithms, but increasingly lately, people will combine conventional processing with neural processing. The systems, basically, conventional optimization algorithms are very computationally intensive, very iterative. The accuracy was a little bit iffy, but they had high flexibility. They could be used in a wide variety of situations. Different neural algorithms have these trade-offs between how fast they are and how accurate they are. But basically, they're all substantially faster than these iterative nonlinear algorithms. You see that kind of here with this is video snapshot compressive imaging, which is like measuring doing the same mathematics but reconstructing time as the third axis instead of wavelength. This is spectral. You see that the gap was a projection-based algorithm with a total variation constraint from original kind of compressive sampling. That would run at 35 seconds or so. So the neural algorithms are basically like 1,000 times faster at doing the same kinds of reconstruction and produce, in this case, 6 dB improvements in image estimation. And then the deep unfolding is neural algorithms that are not specific. They're basically neural denoising algorithms applied, and they're both faster and more accurate and more flexible. So there's a lot of space to kind of think about how to build neural algorithms to do this kind of reconstruction. Looking at kinds of image performance. In this case, this is compression ratio of 30. What that means is, now in this video version of this technology, so with a hyperspectral system, you use a prism to move the code relative to the spectral planes. For video, basically you have a mask that you copy an image of a mask. You move the mask during the exposure, and then each temporal plane is encoded on a shifted version of the same mask. And so this is reconstructing 30 frames of video from a single recorded frame, and then comparing end-to-end neural processing, kind of a state-of-the-art nonlinear optimization, single snapshot imaging system, and a deep unfolding system. Basically, there's nothing to see here. They all look fantastic. So the only difference between these algorithms is kind of how fast they are. But it's interesting how good they've all gotten. And this is the same thing for a spectral compressive imaging system. So the compression ratio is kind of the number of spectral channels here, and all of them do a fantastic job of doing the reconstruction. Now the neural systems. So this is a form of compressive measurement. Compression is possible in measurement systems because images are compressible, which means if you just go and measure pixel by pixel in an image, that's an inefficient way to make a measurement because you're making way too many measurements. But if you want to do less than pixel by pixel, you need to do group testing. You need to combine the images, you need to combine the pixels in groups in a way that allow you to estimate. Compressive measurement means you're going to make M measurements. Or let's say you have a megapixel image, you're going to make 100,000 measurements and estimate the megapixel image. If you do that in a maximally compressive way, you lose the image sense of the measurements, that the measurements are going to be random projections which are not ordered in any way. Such measurements are not appropriate to feed into a neural network. A neural network, neural networks, artificial neural networks, first of all, are very different from biological neural networks. They're not about to take over the world. Arbitrary general intelligence is not threatening us, but for image processing, they are transformative in ways that I'll talk about just a little bit more during the talk. But the input to a neural network that's an image processing neural network has to be an image. That the data is already in kind of image format, which means it's ordered in an image-like way. So you have to do some initial processing to make sure your data can be presented as a kind of rough image. And then basically the neural network is a cascade of filters that are going to look for features in the image. So you have a convolutional neural network is going to take, in this case, it means 64. That means you're going to implement 64 different filter functions on the initial image stack. And then you're going to threshold those with this next block. You have a activation function that's going to threshold the image data. And so you basically have implemented a bunch of filters on it, seen what kind of features exist in the image. And then you take those features and say, I'm going to analyze those features and recast a new image. You go through a whole bunch of different blocks of that, and you can recast your noisy or structured or coded data into an estimate of the scene. And you use convolutional back projection as a method to go through and set the weights in this kind of system so that you'll do the kind of image transformation that you'd like to do. So I'm teaching a class this term on computational imaging, and I was telling the class that today's lecture is like a 1-hour version of the class. This is something that I showed the class today because we were talking about this exact topic, that what you're trying to do with this neural system is kind of imaging. Basically, image processing is a process of pattern substitution. That you have the measurement data that's in a kind of image format that you want to turn into your processed estimate of the scene. A simple way to think about that is as a matched filter. You have a scene, in this case, with frowny faces. You can convolve with frowny faces to match filter, so you get like a pattern of peaks that correspond to where there are frowny faces. The activation function in a neural network thresholds that, so now you have points at the points where there are frowny faces, and now if you convolve that with smiley faces, you transform the frowny faces into smiley faces. So when you want to do general image processing with codes, you're trying to do that in a way where you have a bunch of logic you're applying to all kinds of different filters in a much greater complexity. And so most image processing systems end up in this kind of UNet structure. In artificial neural networks, there are only 5 or 6 basic architectures that are useful for anything. The UNet is the one that is useful for image processing. So basically, you take your input data that exists in your measurements, and what you want to assume is that you're trying to find the features in that measurements you could use to recreate the image, and you need to kind of squeeze the data. Basically, you go from wide and thin, meaning that you have, like, let's say for a snapshot imaging system, you have a single image you're putting in. You're going to try to turn that into a volume image at the output, but you want to try to find the features that indicate what is the image you're trying to reconstruct. And so you go from a few filters in the first layer, and then more filters and smaller image cross section as you go to successive layers, and then lots of filters in the middle where you've identified a bunch of features that you want to image, and then you take those features and you build them into this replacement image that is your new estimate of the scene. Now these bars that go between, those are residuals. So to keep the network kind of honest, you feed forward in each layer the image from the image of a similar size in previous layers. It reminds it that your data should look kind of like your measurements. So you feed that forward and it stabilizes the learning process. Okay, so that's sort of like what compressive tomography is, how the neural stuff changes it. I'll talk more about how neural stuff changes it a little bit later. Basically, the neural stuff can do stuff that's just conceptually different. The algorithms, first of all, process images in very powerful ways. But the previous work that I showed you, was based on this sparsity constraint. Basically, you have an image, reconstruct it in a way that is as sparse as possible, and that gives you fantastic results. But with the neural system, you can do like implicit constraints. You could say, I know the image consists of surfaces. I'll show you in a second what that means, but only estimate the surfaces, and then the neural system has as its prior kind of structural thing to incorporate things you know about the structure of the image. The neural system can do things like the planes that you put at the end of the input. One plane could be visible, one plane can be infrared, and it can give you a joint estimate of the scene based on infrared and visible data, which there's no physical way to explain how that's possible, but logically it makes sense to you that the infrared and the visible scene should somehow be correlated to each other. So it allows you to do just structurally different things. But now I'm going to reach way back to 2009. So 2005, we first started working on these ideas of hyperspectral imaging, and if we do this coding, we could do snapshot, volume imaging. And we thought, well, wow, that's exactly what happens with X-rays. It's just with X-rays. So instead of a hyperspectral image, we'll imagine we have an X-ray source, and we illuminate through an X-ray source through a coated aperture. Mathematically, we could do tomographic X-ray imaging the same way that we did hyperspectral imaging. X-ray imaging turns out to be, just a rich and fascinating area. Basically, you have an object. You can illuminate the object with rays. So the computational imaging challenge is to say, what order should you use the rays? Which rays should you use in what order? And you can measure the attenuation, but you're also interested in the scatter of the rays. Now, in current tomographic systems, usually scatter is just regarded as background noise, and you try to filter it out. But if you do the right kind of coding, you can treat the scatter as signal and improve your estimate. And then you have multiple kinds of scatter. You have coherent scatter you could use for molecular identification. You have Compton scatter that just gives you a broad illumination, and then you have fluorescence and decay and other sources. And so it's a very rich, coding environment, which you might think is kind of simple because it's just geometric optics, but it turns out to be pretty rich. And then through the generosity of the Department of Homeland Security, we were able actually to go build some X-ray systems. So we built a snapshot, a two-dimensional imaging X-ray system with a fan beam. We again use the coated aperture, so you get this kind of textured data. And then from the textured data, we reconstruct the name of my former employer made out of plastic. Just to show that, again, we could do this kind of snapshot imaging. We put an alarm clock in the X-ray system. And then snapshot imaging, we could image in single steps. So we could watch the second hand on the alarm clock move because we were reconstructing each plane in a single snapshot. So this was all work, prior to the neural processing. One of the things that we were interested in, so when you build a computational imaging system, it's not enough to say, I built the imaging system and look, I can use a computer to do the inversion. You have to say, among all possible imaging systems that I could have built, this was the best one, that something was optimal about this. And so certainly one thing that I hope to convince you is that we can do compressive measurements, meaning we don't measure all the data and we can still reconstruct the scene. But then we have to convince you that compressive measurement is a good idea, that you should deliberately go out and do compressive measurement. And so, for example, when you go and take a X-ray CT, basically, CT works typically with a fan beam or a cone beam. From an information theoretic point of view, I can convince you that neither of those is a good idea because you're sampling a smooth manifold with highly correlated data. So if I sample kind of more random rays instead, you get more information per array. And then, so like with a CT system, there's a cost for a array that basically, at the same time as you're diagnosing your patient, you're killing your patient because X-rays are a deadly thing. And so you would like to minimize the exposure you give to the patient. This actually is a real challenge, like with cardiac X-rays. You have to balance the odds that you're going to kill the patient from the X-ray versus the odds you're going to detect something that you would like to cure. And it tells you how often you want to use an X-ray. So if you could use compressive measurement to get the same data with less exposure, then you can X-ray more often and cure more people. So we had a paper, I guess 7 years ago, where we looked at this and looked at the structure, and then but I've been looking at it again recently, and the thing that so first of all, we do subsample data instead of measuring all the radon projections. We can say we're going to subsample. If you do linear reconstruction, these are just simple objects for testing. You do linear reconstruction of the objects, trained with a neural network to do the reconstruction. We can reconstruct extremely well by doing the neural post-processing. What this is comparing, though, is a neural network trained to recognize handwritten digits of where you have a few thousand that you go and train the network with. And you push the network to the Poisson limit of where your noise is starting to kill the network reconstruction. So this is a 10x compressively sampled system at the top and a fully sampled system with the same total exposure at the bottom. And what in this particular study we were able to show is that the compressively sampled system gets a better SNR at the limit of measurement than a fully sampled system. So what that tells you is you get to an environment where not only is it possible to build a compressively measured system, but that it's a good idea, which is not surprising because this is an issue of what is the optimal measurement strategy, and the optimal measurement strategy is never sort of sequentially go through and measure all the data. The optimal strategy is do something that maximizes the information rate. Just kind of continuing just very briefly on this X-ray sort of thing, the X-ray space, again, is very broad. You have the ability, your sources are pretty simple, just like a point source, but you can put a code both on the illumination side and on the detector side, and ultimately you can do some things even with the detector to do like X-ray spectral imaging and all kinds of interesting stuff. The purpose of the coding, you want to maximize the information per photon. You might want to, one thing about using coding, you don't have to think of the system as either measuring attenuation or scatter. You can jointly measure the scatter and the attenuation at the same time, and then you can do things like coherent scatter for molecular identification and other kinds of things. Just as a simple example about how you would go through about designing this kind of system, this is again something that we're going to talk about a couple weeks from now in this course. We have a two-dimensional object. We want to design a coded aperture with a one-dimensional detector array to image the two-dimensional object with a single one-dimensional measurement, so a form of compressive tomography. The way you would evaluate these kinds of systems is then you go and look at what does the forward model look like. This system uses a coded aperture, which people are used to the idea that you could use coded apertures for two-dimensional imaging, but you can also design coded apertures in ways that produce nice codes for three-dimensional imaging. So you can jointly do range and cross-range imaging by the right kind of code. To evaluate a computational imaging system, this top thing is an image of the forward model. In this case, I'm assuming 128 measurements of 780 sort of object pixels. We're going to try to reconstruct the object from 128 measurements of 700 pixels. This is a kind of looking at the overall certain pattern of what that linear forward model looks like. You can also what does each measurement look like on the object space? In this case, the object space happens to be a 28 by 28 pixel grid, and this white is sort of the map of which pixels are mapped onto the measurement in each measurement. And so because it's projected through a coded aperture, these are all projections back onto a point detector. This is kind of the naive way to look at what the individual measurements look like. when you design a code aperture imaging system, you're usually interested in what are the underlying components that you're measuring, which you would use singular vector analysis to look at. So this is looking at what are the singular vectors of this measurement. And what you see, because it's measured from one direction, you tend to have high frequency. You have better range resolution the closer you are to the detector. So basically you have higher frequency response close to the detector side, but some range response even far away, and the lower singular vectors are lower frequency and higher ones are higher frequency. But you take this kind of 128 measurement system and try to reconstruct a 700 element system. You need to do linear inversion first, because the neural network can't really work on the projection data, which is not structured in any natural way. So you do a linear projection to get a kind of quasi-image, and then you do neural processing on the quasi-image to recover the actual image, and you get a very, very good match. Okay, so that's kind of a toy problem that shows you the kind of process you go through to think about these kind of compressive measurement systems. The summary for X-ray systems, compressive tomography, basically, first of all, this idea of compressive measurement for multidimensional systems is revolutionary to all tomographic systems. And it turns out, actually, that almost all imaging systems can be thought of as tomographic systems. So this kind of coding strategy, basically, almost any imaging system you think of, your measurements are embedded in a lower dimensional space than the data you're trying to reconstruct, because you always have time, at least, as one of the data variables. And ultimately, this kind of thing transforms the way you think about any of these measurement systems. But certainly, in X-ray systems, you can get 100 times faster data acquisition, 10 times reduced exposure, more specificity in the measurements. So it turns out to be just a very powerful thing. So the same basic mathematical strategies apply in diffraction tomography, which would be millimeter wave, terahertz radar, and holographic imaging. And now in this case, the coding is really going to come from propagation. That you have data planes that are encoded by the fact that the propagated field is kind of the Fourier transform of the object. But you could add coding elements as well to add a little bit more diversity. So, obviously I used to teach holography for years and years, and I would always come to the class and say, is a hologram a two-dimensional or a three-dimensional thing? And people think of it as three-dimensional because it's like a window you can carry in space. You can look at the object from different directions and see it as though you were looking through a window. But it's a two-dimensional thing. A hologram is a boundary condition. It tells you this is the field on that boundary. And so there were all kinds of great papers in the 80s and 90s about how you could not use a boundary condition in diffraction tomography to reconstruct a three-dimensional object because it just doesn't have enough information. And so I was out for a run in 2008 or something. I thought, wow, that's not true. That if we apply compressive constraints to that boundary condition, we can reconstruct a three-dimensional object from a two-dimensional measurement, because the boundary is actually a manifold in the three-dimensional Fourier space, and if we apply these sparsity constraints, we can do a full 3D reconstruction. And so we did that, and we chose a sparse object. So the object was some dandelion seeds. And so we have these dandelion seeds that were at several different ranges away from the detector. We measured a Gabor hologram, which is that thing that's up in the upper left. And then that Gabor hologram basically tells us the field. We can take that field and just backpropagate it in space. And if we do that, you get this, because the field is non-zero everywhere in space. So if you just measure the hologram and propagate the field back, you get kind of garbage everywhere. But if you take the backpropagated field and apply a sparsity constraint in it, you get a volumetric image from a single two-dimensional measurement. So this is what I got the Gabor Award for, was that showing that we can make a single two-dimensional measurement and reconstruct a three-dimensional volume. And then, same as always, we're not giving up time anymore. So we built a microscope, and so this was what you see through the microscope. We're looking at some water bugs diving through a pool of water. And so this is the hologram, the holographic video recorded, just a Gabor hologram of these water bugs diving over each other. And then we take that data and look at the interference fringes and process it with the sparsity constraints. and you get this video. So this one is color-coded. The red is close and blue is far away. So this is a three-dimensional video of these water bugs diving over each other. And again, just reconstructed with decompressive inference from each frame. This space, subsequently, we and other groups have done a lot of different things. We did a lot of work with millimeter wave versions of this tomographic imaging. But recently, Chungyu Huang, who's working here at Arizona, has been working on variations of this system, and we're working on a wide variety of very interesting ways to think about diffraction tomographic imaging. One of the ones that I'm super excited about is the way that we can use neural processing to incorporate a prior. So like you saw in that video, the hard parts about diffraction tomography, number one is how to deal with speckle. So these neural algorithms allow us to, the same way as you can blur out the speckle, we can think about using neural algorithms to remove speckle from these scenes. But really the hardest thing about diffraction tomography is understanding the relationship between the field and the object. Basically, so as I showed you with the reconstruction of those dandelion seeds, we get the dandelion seeds without having the three-dimensional field. That's the key thing, is how do we build a system that will take the data and not reconstruct the field, but reconstruct the object that caused the field. Now, with a conventional physical system, that's just extremely difficult to even think about what that means. But with a neural system, you can say, I think that, I can just train that this is a relationship between an object and the field, and I'll estimate the underlying field from the measurements, or I'll estimate the underlying object without even really necessarily understanding what the field was. There's basically three interesting ways to think about the field-matter interaction with diffraction tomography. One is you can use the Born approximation, which kind of assumes a linear scattering model throughout the volume. You can use the Ritov approximation, which assumes kind of a phase modulation for the propagating field. Or the one. So those are both super interesting if what you want to do is like biological microscopy and imaging in a volume. A lot of things that my group is interested in is remote sensing, where we're assuming that we're scattering off of an object through an intervening space. In remote sensing, we're not really interested in imaging the volume object. We're interested in the reflections that we're going to see occur at the interfaces, occur at the surfaces of the object, and we want to reconstruct the 3D surface of the object. What you can do with a neural system that's super interesting is you don't have to even think about volumetric imaging. You can just say, okay, I'm going to measure the field, and I'm going to estimate the range in every pixel to the object. So we have some preliminary experiments where we've been working on this, but a lot of what's been done is in simulation. And these are simulations that Chungyu has developed showing that this works great. That we measure the remote field, we give a constraint that we only want to reconstruct the surface volume, and we get a very well-resolved depth map for the object. So in the diffraction tomography space, so I would say kind of stay tuned. We have a whole bunch of interesting things that we're working on. I want to turn now to working with kind of conventional cameras and the things that we can use with
Diffraction holography. You're not using a reference beam that would help you backpropagate and find all the objects.
Well, the reference beam would help us isolate the field. It helps you say this is the field. It doesn't really help you with backpropagation. You can isolate the field from the non-interferometric terms with the reference beam. But once you have the field, it doesn't really matter how you got it. You get a volume reconstruction of the field instead you estimate the field, not the object, if you backpropagate.
So you don't need the reference beam. You see interference with different parts of the object.
That's a good question. It's a separate issue, but you don't need a reference beam. There's a coding strategy kind of thing, and under a wide variety of contexts, among the other things that the neural system can definitely reconstruct the three-dimensional object, but it also helps you remove the reference beam remove the background terms without needing a reference beam. Okay, so that was like, we had this 2007, 2006 or something, we were coming up with this coated aperture spectral imaging. Then we did some X-ray stuff. And then we were like sitting around saying, mathematically, it's a very different thing. But if we just had a camera, it's the same as the coated aperture spectral imaging system, actually, just without the dispersive element. We just have a coated aperture we're going to image on, then we're going to relay the image of the coated aperture onto a detector. The only thing that we did interesting was we moved the coated aperture during the exposure. So what that means is that different time slices are seeing different parts of the code. And so this is mathematically identical to this spectral imaging, but this one, to be honest, it seems like magic to me. So we record this one frame of recorded data, and from that one frame, we apply these kind of sparsity constraints, and we reconstruct this whole video. So this single frame, this is Patrick Ewell's eye blinking. So his you see that glint in his eye kind of opening up. That entire video is reconstructed from this single frame. So for some reason, it wasn't that amazing to do it for spectral imaging, but you do it for video, it's like, really? And then then you can use RGB cameras in motion, and so every time you see a jump on the left, that's a new frame recorded, and then the video on the right is reconstructed from those single frames. Same thing here. But this is data from 4 or 5 years ago, so processed with conventional sparsity constraint kind of reconstruction. This is data doing the same thing, but very recent. Again, you have the single recorded frame, and the entire video is reconstructed from that single frame. This is this total variation compressed sensing kind of approach. This is a neural denoising algorithm, and so the increase in dynamic, you go from 26 dB to 30 dB fidelity with the image, and you've increased the effective frame rate by, in this case, I think by around a factor of 100. So you do 30 frames per second, and you get 3,000 frames per second video. Now, this kind of thing, first of all, has been very useful for ultra-fast systems where you can record, ultra-fast phenomena at video rate with this kind of coding. But there are ways to combine this with kind of optical electronic processing in very powerful ways that allow us to rethink what we think of as video, that we can kind of reconstitute measurement in ways that we can get efficient with pixels and video. Again, this is the same processing from Xinyuan's work. We get in this case, a 7 dB increase in fidelity using the neural processing, and again, the entire video is reconstructed from the single frame shown at the left. Once you have this kind of platform, then you have a platform you can do all kinds of interesting processing. For example, so what we're saying is that we can reconstruct multiple video frames from a single exposure. If you sweep the focus of the lens during the exposure, then basically you've done a focal stack in a single exposure. So instead of having the motion, you can, in this case, this entire focal stack of an image is reconstructed from a single frame. And so this becomes a platform that you can actually encode, that you could think of as you're changing things about the camera. You can encode spectrum, polarization, time, all on a common sampling platform that you reconstruct. And the goal is to try to think about how to measure that as efficiently as possible. Yeah.
When doing the experiment, what was the most sensitive constraint in terms of the aperture itself, spatial, or how long you did the exposure?
No, I mean, the number one thing with these kind of experiments is figuring out how to calibrate the system. You have to have a mathematical model and how to do that inversion, and so there's a black magic involved in relating your images of the system to your measurements and what is the calibration. Yeah.
Moving in time that occurs during your exposure, right?
Right. So the code is moving during the exposure, back and forth. So the image is going back and forth at 30 hertz. But you basically, if you want to reconstruct 100 pixels, the code has to move by 100 pixels during one exposure. Okay. So that's exciting and cool, but really, yeah.
So in terms of information transmission, all that's in one frame. So if you take the amount of information there and how much resources are required to transmit that, and then compare it to maybe a typical video compression algorithm as seen, is it a net win, or is it just a different way to skin the cat?
It's not a net win. I mean, this kind of physical compression is not as efficient as the most efficient digital compression strategies would be, because they can. A digital compression system doesn't have the constraints of kind of blind compression. If you do image-specific compression, you could do better compression. So here, we could be doing like a factor of 100 compression, but a advanced, a digital compression system might be able to do a factor of 1,000 compression. The ability to do this is based on the fact that a video system is not anywhere near its information capacity in terms of sensor capacity, so that you can do this coding because images are compressible, so that you have a channel that's underutilized, and so using the code you can get closer to the channel capacity, but still far away from the maximum channel capacity, I would say. But that leads actually to the next question, which is what is a good measurement? Given what we know about these neural systems, the systems that we built here are kind of based on the fact we have a data cube. We want to compress, but we want to be sensitive to the whole data cube. So if you do things like with hyperspectral cameras, you have the possibilities of measuring plane by plane with a tunable filter or with a push-broom system. When you do that, you're insensitive to everything outside of that plane. So the information far away from that plane won't be sensed. By going to these kind of spatially modulated pixel filters, you've combined the data in a compressed way, but you're sensitive at some high resolution to every point in the data cube, and so you have the possibility of doing the reconstruction. When we go and analyze these systems, typically we like to look at, what are the underlying eigenfunctions, the singular vectors that sample the system, and you'd like to see, this is random projection versus, sort of systematic radon projection, and what you see with the random projections at the lower orders, you see much higher frequency response, which indicates that for fewer measurements you might be able to get high resolution, high frequency response. But when we go to these neural systems, things change a lot, because you're interested in how can a neural system infer the data? What kind of data does it need to infer? And we're not really, these are all maps on the pixel space, but images are not encoded on pixel space. Images are encoded in whatever natural image space there is. So you're really more interested in what does the data rate look like, or the sampling look like on the sort of underlying features that really represent the image. And in that case, I think that things like multi-scale sampling can come to play in a lot more sophisticated way. So with conventional processing, first of all, the conventional compressive system, we have data that's already represented, with a linear operator, and we're just trying to sparsify that or operate with some constraint. With the neural system, you really have a much more general and hopefully like a Bayesian estimator, where you present a bunch of data and it says, based on all the data you've presented, this is what the scene ought to be. And the data doesn't have to be related in any kind of simple linear way. You can build a very general sort of processor, but you need to create it in a way that exists in an image sort of format. Just to give you an example of ways that we've been thinking about doing that, this is again from a paper that came out earlier this year with a collaboration with a group at Tsinghua University, led by Fan Liu. We looked at building camera arrays, and so I'm interested in sort of what are ideal sampling strategies for array systems. But this is a multi-structured, not a sort of like measure each part of the field and reconstruct camera array. It's a camera array that has a kind of wide field camera and then a lot of narrow field cameras. And so with the narrow field cameras, you can find points of interest and reconstruct those at high resolution without having to sample the entire scene. So this is a kind of powerful strategy for kind of camera sampling. That basically with a camera you have this kind of pyramid of data, of the data cube, of how much spatial resolution, what kind of field of view do you have, what kind of depth resolution do you have. And, you could, in principle, build a system that would just sample everything, but that would be extremely inefficient. So you say, well, how would I structure my sampling data in a way that would, get me specifically the data that I want in the most efficient way? So that is, again, sort of like a model for general ways to think about tomographic imaging. We basically, again, tomographic imaging basically is all imaging because you always have a data cube and you always have some sensor resources, and your question is, how should you manage those sensor resources or arrange them in a way that allows you to maximally get the data you want out of the data cube? Again, this is from a group paper that the students who are here in the room published earlier this year on using deep learning for camera autofocus. So camera autofocus is just one aspect of the robotic control of a camera. So if we have this heterogeneous cameras array, we can imagine ways to deploy the camera resources based on the scene to reconstruct. And the idea is get all the information in the scene by using a neural network now, not just to do the image estimation, but also using neural network to control what measurement to make next. So if you had an X-ray system, or you have any system you have, basically you have some sensor resources, you could deploy those, but you could also say, based on what I know so far about the scene, what's the next measurement I should make? So this system used a reinforcement learning process to basically look at the scene for a camera. And first of all, we take the stack of data that we've measured so far and don't create, we don't present the image from the current frame. We present our estimate of the all-in-focus scene in every frame. And this is a thing that is really where we want to go with compressive tomography, is that we're not saying we want to reconstruct each frame in a snapshot. We want to control the system sequentially so that we actually have the full space-time data cube reconstructed in every step, but we're making the optimal measurements in every time step to perform. So this agent says, based on the current scene, what is the next focus position that you should go to? And it doesn't choose like the focus position that gives you the best current in-focus image. It says, well, this background part I've already know pretty well in focus. This other thing seems to be moving. Go lock in on that, give me data from that, and whichever part of the scene is most blurry in your current estimate, the next step, go and make a measurement there. And so the networks to do this, then become pretty complicated because you have, something that will look at what is the quality of the image based on, which part is most in focus, and then take all that data and predict what is the next focus position that will give you the best estimate of the all-in-focus scene. And then this baseliner is something to check sort of there's a reward function for the system to say, basically you're treating focus as a game and you're rewarding the system based on, has it developed a focus strategy, basically a game playing strategy that gives you the best all-in-focus image. And so, Chen and Huang and Chengyu Wang were able to build these kinds of systems and not just produce, well-focused image, but all-in-focus video. So all the frames that are estimated by the system are in focus, and the game playing aspect of it is come up with a strategy that, among other strategies, would give you the best all-in-focus image. And so this is kind of showing what this looks like. The top thing is the map of where the system is choosing to focus in each time step. And so then the measurement frames, you see some parts of the frame are in focus, some parts are out of focus. But in the reconstructed video, the entire scene comes out in focus. So, what I hope I've shown you today is that the ideal sampling system can make a big difference in the kinds of measurements. The way that we do this processing in adaptive sampling and control is kind of very revolutionary for imaging systems, and in particular for these tomographic systems. Now I would say that we don't really have a good idea of what the optimal focus, or what the optimal sampling strategy is, because we don't really need to think necessarily about this kind of mosaic sampling that we did with the early compressive measurement systems. Now thinking about like multi-scale, multi-dimensional sampling schemes are increasingly attractive. I've shown you a bunch of examples from different kinds of imaging systems, but basically the same methodology applies essentially to any kind of imaging system and opens pathways for many new ideas for design. Just to give you one idea of where that's going and kind of to presage Professor Drigger's talk from next week, one of the things that we're very interested in is combining infrared and visible. This is, we were out with Professor Driggers in a truck a couple weeks ago and took some shots of panoramic shots of Tucson that are stitched together with long wave, mid wave, SWIR, and here near infrared and visible. You see a lot of differences here, and what we're, Ming Hao and the team are really working toward is how do we combine these data into integrated frames that would build on this idea of adaptive multidimensional sampling. So Ron, I've stolen all your best stuff from next week. I don't know what you're going to do now. Thank you all for your attention today.
Questions?
So with your neural nets, you get the images that you have taken with multiple masks or multiple cameras. At what point do you introduce the information about what mask you use, at what instant of time the mask came in, or where the cameras were? How does that information get into the neural net?
So basically the neural network, you have to define, these are supervised learning systems, so we know the input and we know the output. So basically we know the forward model, we know the mask, and so we know how that takes a known image and produces coded data. The powerful thing about, so when people talk about neural networks, people always say, well, it's a big data problem, that you have to get lots and lots of data to train the neural network. For imaging systems, I don't think that's the right strategy, because it's very, very difficult to get like natural data that you would use for training. Basically, there's an asymmetry here, that the forward model for these systems is very well characterized, and we don't really know the inverse algorithm. So we can do very good transfer learning. We create a model system that we can create artificial training data, code that data with our model of how the mask works. Now, in the actual physical systems, the masks are imperfect, so you want to make some measurements to characterize exactly what the physical system is doing to get the calibration. You use that to encode synthetic data, and then in the synthetic data, you know the ground truth, and you can train the neural network to do the inversion. So you have to know both the sort of coded data and the ground truth data.
For the hyperspectral system, is the coded actual always fixed by fixed, the distribution of the binary 0 and 1? It have to be fixed.
Well, so my group only used fixed chrome on glass masks. There are other groups that have done adaptive masks, where you use like a spatial light modulator to you could dynamically change the mask if you had a spatial light modulator.
Then, if we can add some variation on the mask, does that exist to maybe optimize the mask which can?
Yeah. If you change the mask, you could optimize the measurement to the environment. You could improve performance.
Processor mask that does both spectrum and time?
Yeah.
Can you do
Yeah, we have done that.
Okay.
I mean, a simple way would be like make a mask that has color filters on it.
How long does the reconstruction take in comparison to how long the exposure is?
Well, with these the original decompressive iterative algorithms, to make that. So if you look at this video, it was recorded in 5 seconds, and probably took 5 hours to process. But then when you go to these, I guess. So you go to these neural algorithms, and the reconstruction time is literally like 1,000 times faster. So you're pretty close to being able to do it at full frame rate.
Can you describe how the coding mask enables measurement of static?
Measurements of what?
From scattered light?
Yeah, so so here you have an object. You're going to see scatter. Basically, each point in the volume is going to produce a different pattern. And so by analyzing the patterns detected here, each point in the volume ideally produces a separable code that you can use to identify where that light came from. So without the code, you just have light. You don't know where it came from. Basically, if you had a pinhole here, of course, then you could say that the light came along whatever direction it was imaged along that pinhole. But that doesn't give you any range resolution. By having a full two-dimensional pattern, you can get both cross-range and range resolution in the pattern that you measure. Yeah.
I have a weird question. You said something early in the talk about as long as you represent your data by an image, then you can do some of these things. And it makes me wonder whether is the big data community being informed by some of the concepts of image analysis, or is it vice versa?
Well, big data. There's big data is everything, right? So they look at all kinds of things. So certainly.
Do they try to represent data in image-like format in a way that they apply some of these concepts, or?
No, I would say if data doesn't have some kind of underlying spatial structure, I mean, no, I would say, in one sense, yes, definitely. Like if you do unsupervised learning, you look for sort of patterns in data that ultimately can be interpreted as images. So yeah, there is some versions of that where but to represent it as an image, you have to assume that there's some kind of distance between points that makes sense for you to do some kind of mapping. Well, I mean, aspects of it are certainly working together. I would say image processing, the stuff that I'm interested in, is a tiny subset of the overall big data community. But the neural networks basically it's the new software. It's like if you want to do any kind of processing, using a neural network makes programming easier. So the sort of, I guess, the ratio of image analysis to all processing is kind of the same as the ratio of image analysis to all software.
You take a frame of a scene and you predict almost what the future holds for the scene. Are these methods being employed for doing things like, to piggyback off of that question, things like stock market analysis? You have an instance in time and you'd like to predict, maybe 2 hours of the future, or in the extreme case, in the extreme opposite case, maybe like time dynamics of galaxies, where instead of the frame being a fraction of a second, the frame is.
Right. Well, I mean, 100%. You can do that, and I would say that's kind of the basis of self-driving cars, right? You use this image analysis to predict, what's going to happen or what you should do with a autonomous control system, for sure. I mean, and like with the focal control system, you're kind of trying to predict what is in the next scene. Where do I want to focus? That's predicting the future.
Reinforcement learning, what kind of algorithm are you using? The ReQ policy or?
And what kind of algorithm are you using?
I used a policy gradient. Yeah, so the decision space is continuous. So we can't come up with a table to store all the possible states. So the policy gradient really helps make the decision space to be continuous, and use the gradient to guide which states it should go to next.
Thank you all.
Thank you.